Yeah, so hello everyone, and thank you for joining. Um, Today we have Dr. Shah Faisal, who will be giving an introduction to variational calculus, and you all know him very well. He's a postdoctoral researcher at Uppsala University. He recently joined there. Maybe he would say a few words about that if he wanted. And yeah, so let's hear from Dr. Shah Faisal.
Yeah, thank you very much, Dr. Wajid. I have come to Uppsala before 2 weeks, and here I joined the Center for Geometry and Physics in the University of Uppsala. And I will be here for a good amount of time in the future. All right. So in this talk, I want to tell you about calculus abbreviation. And to do so, first I will give you some interesting motivations that comes from problems that are very important in the real life. And then I will introduce you to the theory of calculus abbreviation. Especially, I will talk about some modern methods and techniques that are used in practice. All right. So, what is variation calculus about? So, you take a Banach space X, and for instance, you can take the Euclidean n-dimensional space Rn. You can take some function space, let's say LP space, if you like. And then you consider a functional I. So a function, by function, I mean just a function. So I is a function from X to R. And the question we are interested in is to see if the given functional I has a global minimizer. And a global minimizer is basically a point in the domain such that the value of the functional is the smallest at that point. And the second question we are interested is that, well, if such a thing exists, can you compute it or can you approximate it at least numerically? And so calculus abbreviation is basically answering these two questions for functionals. So that's the main goal of the variational calculus. In the literature, if you look out, um, there is this terminology called the variational problem. So a variational problem is a problem where you are trying to minimize or maximize a given functional. Okay. And so by this logic, calculus abbreviation is studying variational problems. Now the question is why you should be doing this? Why you should look for minimizer of function. So before I do that, I will consider a class of functional, which are very important. I mean, you can write down a lot of them, but the most important ones are the following. So if you take a domain, omega and Rn, and suppose the boundary is smooth enough, and then you take a function u naught, so the given function, which is C2 function, is twice differentiable. And then you look to, so you define X, which is the space you're looking in, to be the functions from this domain to Rm, some other Euclidean space, which is C2, so it's twice differentiable. And on the boundary, it agrees with the given function you have fixed in advance. And it gives you a subspace of C2 functions on the domain omega bar to Rn. And we consider the following functional on this space. So you take some function small f, which is defined on omega times rm times this to r. And the function is doing the following thing. So you take a function u from the space x, you plug this function and its gradient, which I have written here, in f, and then integrate over omega. And it gives you a well-defined real number. Well, if small f satisfies some good conditions. And we are interested to minimize this function for different choices of the space x. And I mean, this class of function is really important. In most of the practice, these kind of functions appear, but they're not the only ones. But in this talk, I will restrict to this case. Okay. Now, the question is why you should be looking for minimizers. The reason is that a lot of problems in real life can be formulated as problems involving the minimization of some suitable functionals. You try to solve a problem that is very interesting for real life, and then you do some math with it, but it boils down to minimizing a function. And so let me give you some example of this phenomena before I go into the theory of calculus evaluation. So let's consider a problem in geometry, and you do the following. You fix a closed curve in space R3. So C is a closed curve I have drawn here. And what can you do is you can find surfaces with boundary on C. So you can fill this curve in the space with some surface. And you can do it by different choices. For example, you can take one surface like this and then other one that goes like outside, but still has this boundary. And you can find a lot of surfaces to fill the given curve. And the question is that if you are given the closed curve C, what is the surface of minimal area? So, I mean, each time you get a surface with boundary, the given curve C, it will have some area, but what is the surface with the minimal area? This is a question in Riemann geometry, and I have written it in a very special case in the Euclidean space. So let's see how it boils down to minimizing a functional. So you place the given curve C in R3, and you find some domain in the plane, which is R2, and the domain is omega. I have drawn it here. And this C I have drawn can be realized by the graph of some function which I denote by u naught. And then if you take any other function u in the domain that agrees with this given function, then the graph would be some surface with boundary on C. So this way you realize the surface through the graph of some function. And in calculus courses, you have studied that if you are given a function on some domain, then you can determine the area of the graph, which is basically this expression. So given a function u, you take the gradient square plus 1 and square root and then integrate it over the domain x. That's the area of the graph. And so now you take a function that represents some surface with boundary on the curve C, and then you assign to it its area of the graph. And that gives you a well-defined function, and you are trying to minimize this. Okay. So we can rationalize this question. So given a domain in R2 and a function u naught, which I think of as a curve in R3. So I look to the graph of u naught, and it will be some closed curve in R3. And then I look to the space of functions which are smooth, but agrees with the given function on the boundary. And so basically these are all surfaces that can be represented by graphs of function and which has boundary this fixed curve u naught. And then you define a function by taking a surface or a function that assign the area of its graph. And the question is at which value of u is functional at n its minimum. So you need to now solve this problem to find out. Okay. So let's talk about some problems in real life now that boils down to minimizing function. In the modern age, so you have seen that there are self-driving cars, and one of the basic principle of these cars are they have some kind of camera system that capture the surrounding and then send it to a processor, and the processor extract information out of it, and then according to that the car respond. So for example, if a car is coming and then is somebody standing in front, the cameras take a picture, let's say, and then tells the car there is somebody. And so in this case, the car is basically analyzing the information coming from the pictures on the car. Another example you take is, well, this is basically a picture of brain tumor, this white place. And to remove this kind of tumors requires surgery. It's a very sensitive surgery. And so you need a high precision in this kind of surgeries. And so a proposal would be to, well, do it with robots. And in order to do that, I mean, the robot, of course, would scan the brain and exactly determine the boundary of the tumor and then cut it. So all these information, the robot would collect using some camera system. So it takes picture, analyze it, and then accordingly respond. So these kind of things are very sensitive to what the picture says when they take it. And it's possible that some pictures, when you take it, there are regions that are corrupt, you can say. So some information are missing. For example, in this picture, like the camera captures this picture, but the information on these regions are gone. And so if you analyze it and act upon according to these pictures, you might kill the person, you might kill the brain of somebody. So it's important that the camera really take the correct informations, meaning that the picture is very good. Okay. It's also possible, for example, you would like the camera to send this picture, not this one. And so the question would be, well, if I get this picture, can I perform something on it to recover the lost information before I send it to the car or the robot to respond? Another thing can happen is this blurs. So camera sometimes take picture, but it's blurry. This is the original picture, and this is the picture with noise. And then you're like some kind of process that remove these blurs. So let's do some math with this problem. So let's go some kind of right. So if I if I consider a picture, then each picture is made of three color, red, green, and blue. And in the picture on the slide, you can see if I move my pointer, the value of green, red, and blue are changing. So each point take 3 values. And if you can remember all these values, you can recover the picture. Okay. So if I pick a point on the picture, then you just saw that the camera assigned 3 values to that. Is the value of red, blue, and green, which are some values between 0 to infinity. And the camera does it to each point on the picture. Now, if you know these 3 values per each point, you can recover the picture plotted by camera. Very well. So now consider this picture to be placed in R2 and think of it as a subset of R2. So it's a rectangular region which I denote by omega. And then each point which has coordinate x and y, you assign 3 values, which are basically the value of red, blue, and green color. And so it's nothing but it's a function that to each point on this domain assign 3 values. So this way, a picture is just a set of 3 functions on the given domain to R. Or you can say a picture is just one function to R3, where one is representing red, the other is blue, and the other is green. If you know these 3 functions, you can plot it and get the same picture back. Okay. So now the advantage of this point of view is that you can do math with it because these are functions. Okay, now let's go back to the picture we have with some blurs. And the picture obtained by camera will have some noise, which is this one. So let's say you note as the original picture. The picture obtained by camera will be this original scene plus some noise that I denote by this symbol. And you want to minimize the noise. Okay. So to minimize noise, well, a picture with minimal noise would be a function, right? So you should look for that picture in some space. So the space of pictures is for me now the space of L2 functions on this domain omega. And you are trying to look for some function that represent a picture with minimal noise. So you need to minimize all these noise. And so the function in this case would be that you take a picture and then assign this value to it. So basically you want that picture of minimal noise to be close to the one you obtain, but then it should not change the color quickly. So you minimize the gradient as well. And there is some other fidelity parameters you need to determine, which says how better you want, how good you want the approximation to be. And so now if you find a minimum of this function, that would be representing a picture with the minimal noise. Okay. And in the second case, you have a picture where some informations are lost on some regions, for example, these scratched areas. And you want a picture that recovers these areas. So let's do the same thing with this picture. So you think of this picture as a rectangle in R2, so it's some region omega. And the damaged area is a subset of omega, which I denote by D. Okay. And what do you want? You are given a damaged picture, which means you are given a function on the complement of the damaged area. So the picture is good here, but it's damaged on here. So here it's not defined. That's what it means. Okay. And you want to find another another picture that is the same with the original picture away from the damaged area. and recover the information on the damage area. So basically, you are interested to find a function that should agree with the given function and the complement of the damage area and should nicely approximate information on the damage area. Okay, so this is basically finding a function again. And to do that, let's consider the space of functions or the space of pictures to be maps that has bounded variation. It's a condition on how the function varies on the domain. And you are looking to the following function. So take a picture and then take the L2 distance with the original picture and the complement. So you need to minimize the L2 distance and the complement of the damage area because you want the picture that recovers the information should be the same on the complement. So you need to minimize the distance in the L2 space. Okay. Of course, you don't want the picture to quickly change the color. For example, if this is here is blue and then you move a little bit to the damage area and suddenly it becomes red. So that's something you don't want. You want the color to be smoothly extending to the damage area, right, from the neighborhood. So you want to minimize this guy as well. And how good you want the recovered pictures be, there's some other integrals you need to look to. Okay. And so if you find a minimizer for this function and you plot it, it will give you some picture which is the same on the complement, but recover information like something like this. Okay. So these were two examples where interesting problems boils down to minimizing functionals. That's what I wanted to explain. Okay. Now the question is, if you have a function, how do you minimize it? What are the methods? So let's talk about some methods now. In calculus evaluation, there are two type of techniques. The first one were based on classical approach, which were developed by Euler and Lagrange, and of course Newton. And the other one is more modern and so it's coming from Dirichlet, Weierstrass, and other people, and it's called modern methods. So let's talk about the classical methods first. Let's restrict to a very simple case, okay? Take x to be the real numbers, and now the function is just a function from R to R, which is smooth, and you want to minimize it, okay? How do you do that? I mean, you have learned this already in calculus. Well, if you want to find the minimizers, compute where the first derivative vanishes. Compute the stationary points. And then you have the second derivative test. Now, once you compute the stationary points, then you check whether they are minimizer or local maximizer or local minimizer. You compute the second derivative, and if the second derivative at that point is strictly positive, that means it's a local minimizer. But if the second derivative is positive everywhere, it means the given function I is convex. Then any local minimizer is a global minimizer. All right. And that's something you have learned. So if you, in calculus of one variable, you know how to minimize or find minimizer for smooth function on R. The first derivative test and the second derivative test. And if the function is convex, then any stationary point will be global minimizer. Okay. And then in multivariable calculus, you learn how to do it for functions on higher dimensional Euclidean space, Rn. The same kind of theorem that works in higher dimensions. But the problem is, if you replace the domain to be something infinite dimensional, Banach space, how do you do that? For example, consider the case where the space X is a space of C2 functions which has some boundary condition. And the function is given by this, which I wrote before, and you want to minimize this function. Now, in this case, you are not in the Euclidean case. So the space is X has infinite dimension. How do you do this one? So we can still apply the previous theorem in some interesting way. So let's do the following. Assume some function u is a minimizer of I. Suppose it. And now I look to the following function of one variable. So take up some function that vanishes on the boundary and add it with the minimizer. So the minimizer plus t times and t varies between the two values, minus epsilon to epsilon. Now it's a one parameter variation of the minimizer, you can say. By varying t, you are just varying the minimizer in the neighborhood. If I compose this with the function I wrote above, I will get a function on this interval to R, which is defined by this, right? Now in this case, I just now work in the intervals. It's a function from open interval to R. And t equals 0 is a minimizer because of this, because u was the minimizer. So you know from the previous theorem in the Euclidean case that the derivative of this function should vanish at 0, right? Because it's a minimizer. So what you have done, the derivative should vanish. And if you compute this derivative of this functional, you set it equal 0, that's exactly what you get. It's a nonlinear partial differential equation in this case you get. It could be linear in some cases depending on functional, but in general it's a PDE, okay? So what does it say? If a function u minimizes the functional I, then that minimizer should satisfy this partial differential equation. And that's exactly the stationary values of the functional I computed. And conversely, if the functional is convex, then any solution of this will be a minimizer. That's what exactly you learned. So in the previous case, where the function is defined from R to R, this equation is just an algebraic equation in X, the variable X. But since in this case, since the inputs are functions, you will get not an algebraic equation, but a partial differential equation you need to solve. And it leads to the following theorem. So consider the same space of function I defined before and the functional we considered before. Then we saw that every minimizer of X should satisfy this partial differential equation. So if you want to find minimizer, you need to solve this equation, figure out what are the solutions, but not every solution will be a minimizer. It's just telling you the candidates for the minimizers. And conversely, if for every X, this function is convex, which is the convexity of this function, then every solution of this PDE would be a minimizer. So that's exactly the first and second derivative test, but in the setting of infinite dimensional Banach spaces. Okay. This is basically a classical approach. So it was done by Euler and Lagrange, and they applied it to some problems. And but this kind of approach, units you see, you need to solve some horrible partial differential equations. So now let's do let's consider the functional that I wrote for the minimal surfaces before. So before we wanted to do the following. So take a closed curve in space R3, and you want to find a surface with boundary of that curve and has minimal surface area. And we we saw that you need to just minimize this functional. So what would be the Lagrange equation for this? If you want to minimize for this, you need to solve that equation. So in this case, the small function f is given by this. And so if you plug this small function to the above general equation, you will get the following partial differential equation. So the divergence of this expression vanishes, and the function has to agree with you now. So the surfaces that are represented by graphs of functions and minimize the area must solve this equation. So if you can solve this equation, you can tell me what are the minimal surfaces. Okay. Now the point is that Lagrange derived this equation in 1762, but he couldn't solve it for any curve. Remember, U0 was representing a closed curve. The graph of U0 would be a closed curve. So Lagrange couldn't solve it for any choice of U0, but he did it when U0 is a curve that can be placed in a plane, so you can pass a plane through it. But in this case, it's just the area filled by the curve. If you take a closed curve in the plane R2, then the inside is just a disk with boundary on the curve. And Lagrange proved that that's the minimal area case. But if you take the curve to be going somehow, it has some torsion, for example, then the PDEs become very complicated to solve. And Douglas basically got Fields Medal in 1936 for proving the existence of minimal surface with a given boundary. He did it in general cases. Okay. So now in the classical methods, I mean, it's powerful enough. It covers a good amount of functions, but it has limitations. The first one is that the minimizer solves some partial differential equations. So function that solves some PD is usually at least C1 functions. So they're smooth functions. So classical method would always compute for you only C1 functions, C1 minimizer. And sometimes you're looking to more general minimizer, which has some singularities, so not necessarily smooth. So you cannot do it with this classical approach. Okay. Secondly, the classical approach assumes that the function is smooth. That's why you can differentiate it. But in real life, you will face functions or functionals that are not smooth. So the classical method would not apply to that. Third is that the classical method depends on theory of partial differential equations. So sometimes you face a very horrible partial differential equations to solve. For example, the one with minimal surfaces, it's a very complicated PD to solve for general curves. And so sometimes it leads to more serious problems in partial differential equations. And so you would like a method or another method in which you don't assume the functional is smooth, maybe something even not continuous, for example. And you want to somehow and find minimizer for those kind of functions. So this kind of method you're looking for. These kind of methods are called direct methods. And so let's motivate it from a theorem that we have studied in topology, general topology course in your bachelor. It's the Weierstrass theorem. Weierstrass theorem. It says the following. If you take a compact metric space Y, then any continuous function attain its minimum vertex, which means that there is a point in the metric space Y at which the function attain its minimum. So the value of the function is the minimal possible. Okay. Let's have a look to the proof of this theorem. So take the infimum of f over y to be some number m, which could be minus infinity, I don't care, but it's something m, okay? and take a sequence in y such that the value of the function along that sequence converges to the minimum or the infimum. Now, such sequence exists by definition of infimum, so you can approximate the infimum of the function through sequences. Okay. Now, since y is compact, the sequence that infimize the function f, as here, must have a convergent subsequence because y is compact. I mean, every sequence in a compact space has a convergent subsequence. And therefore, it converges to some point x naught in y. And therefore, the continuity of the function means that the limit of the function along the sequence equals the value of the function at that limit. But this limit was converging to the infimum by this case, which was m, and therefore the infimum is realized at x naught. Okay, that's the Weierstrass theorem, that if you have a continuous function on a compact vector space, then it has a minimizer, a global one. Okay. Now here actually the continuity is too much. You don't need the function to be even continuous, by the way, in the Bau theorem. If you just assume that the function is continuous from the left, meaning that it's lower semi-continuous, that's exactly what it means. So then it will attain its minimum. So for example, so the lower continuity is defined as follows. If you take a point in the metric space and take a sequence convergence to that point, then the limit infimum of the function along the sequence will be at least the value of the function at that point. So that is basically saying that the function don't jump if you go from left to the point x naught. Okay. Now this is enough to get the conclusion of the Weierstrass theorem, because along the infimizing sequence, I must have this thing because of the lower semi-continuity. But the value of the function at x naught should be greater or equal to the infimum by definition, and therefore it should be equal. Right? So a better version of the Weierstrass theorem would be that if you take a compact vector space y, then every lower semi-continuous function attains its minimum over x. You don't need a continuous function. You just need a function that is continuous from the left. That's it. It might jump from the right. It doesn't matter. But you just need. Now the question is why I'm talking about this theorem. Well, because it's an interesting theorem saying that the function, okay, so it doesn't assume the function is smooth. It doesn't even assume the function is continuous, and it tells me that there is a minimizer, a global minimizer, right? And so it's a very important theorem, but the only problem in this theorem is that it assumes the space Y to be compact, and Banach spaces are never compact. So it's a very good theorem, but in my setting, it's not working because the functional I consider were defined in Banach spaces and they are never compact. So I cannot apply this theorem to those. I mean, it's good that it covers even non-continuous functions and find minimizers for those functions, but only on compact. But now the question is, can you modify this theorem? Remove the compactness and still have something. Okay, first of all, consider an example where a function is not lower semi-continuous, which has no minimizer. So the lower continuity is really important in this case. For example, in this function, it's a continuous from the right, but it jumps, but it has no minimizer, right? So the message is that this lower semi-continuity is really important. You cannot weaken this further. Okay. Now, in order to apply this theorem to the setting of minimizing functional and Banach spaces, you would like to remove the condition of being compact on Y, and then you are all set. Okay? Because Banach spaces are never compact. Now, consider the non-compact space, an example. If you remove the compactness from the above theorem, then the theorem breaks down. So consider that interval which is closed from 1 and then open from infinity. And take this function 1 over x. The function is decreasing, and it has no minimizer because the minimizer gets lost in infinity. So if you just remove the compactness from Weierstrass theorem, you are losing minimizer. So the lower semi-continuous was also very important, but also the compactness. So you need to do something interesting to keep the theorem true while you remove the compactness. Now here, why this theorem fails here. Why the compactness causes the failure of the theorem. In this example, you can see. The point is that the function is decreasing as the value of x in the domain approaches a region of non-compactness. The region of non-compactness in this case is near infinity. So as you go towards near infinity, the function decreases. And so you are looking for a minimizer above any value. So you reach close to infinity, but then the function is decreasing. So you go further a bit, and then you go further a bit to find your minimizer. And in this non-compact region, the minimizer just gets lost. So if you want this theorem to hold, you should do the following. The function should not decrease as you go towards non-compact regions in the domain. If that doesn't happen, it means any sequence that minimizes the function would stay in a bounded region, in a compact region, and then you can find it would a minimizer because it would not get lost, right? And that's basically the motivation behind it. Drop the assumption of and Y being compact. Assume that when you approach the non-compact region, so in a Banach space, it would be near infinity. So as the value of x goes towards the non-compact regions, the function should not decrease, it should grow. So this means that the minimizing sequence would not enter to those regions. Simple, very simple. Okay. And therefore, any sequence that minimizes the function will be bounded because if it is not bounded, the function increases. Therefore, okay. And so if you have a nice condition on the domain, then and every bound, for example, if every bounded sequence has a convergent subsequence, then you are done. Then you will get a minimizer for your function. So the story is the following, or the conclusion is the following. You can drop the assumption in the Weierstrass theorem on the space to be compact. But instead, you should force the function to not decrease in the non-compact regions, which is basically saying that near infinity, the function increases. Then you are all okay. Okay? And therefore, it gives me the following theorem. So consider a Banach space, which is a reflexio. A reflexio is basically those spaces where bounded sequences have subsequences that are convergent. Now consider a functional, and you want to find the minimizer for it, and we don't assume it is continuous, by the way. But we just assume that it is bounded from below because otherwise there is no way to find minimizer. And you assume that the function grows near infinity. That's because the compactness is not there on the domain. So you assume this. And if it is lower semi-continuous, then it would have at least one global minimizer. In all the things I explained already, this condition is because you want to find minimizer. So the minimum should be attainable. You want the minimum to be not minus infinity, for example. Sorry, this is minus infinity. And you want the function to grow near infinity because the space X is not compact, so the minimizer can get lost as you approach near infinity. And the third, of course, that's coming from Weierstrass theorem, the lower semi-continuity, you should not jump. The function should not jump as you approach the value from the left. Okay. If you have all this, then you have. Now this theorem is interesting because it tells you when a minimizer exists, even not caring about the continuity of the function. It's just lower semi-continuity, you know. So now let's apply this theorem to the case we have considered. And you would like, for example, to have this functional lower semi-continuous first. Now, there are theorems saying that this function is lower semi-continuous if and only if this function in the integrand is convex. Okay, so if you start with a functional where the small f is convex, then this function would be lower semi-continuous. And this is one of the necessary conditions for the above theorem to have, or one of the necessary conditions for this function to have a minimizer. It just tells you that how the convex analysis enters through the picture of variational calculus. Okay. And now this gives me the following theorem. So I consider some Banach space and the function, and the function grows. So there's a growth condition, which I assume to be this, because near infinity should grow. And the integrand, which is f, is convex, then it has at least one minimizer. Okay. If you particularize this to this function, this functional, which is the L2 is norm of the gradient, then this function would have one minimizer because it satisfies the conditions above. Now you can use direct methods to solve PDEs now. I mean, in the classical method, you use PDEs to find minimizer, but you can go the other way around. You can now go and solve PDEs by using direct methods. So do the following thing. Consider a partial differential equation, which I call P, and a function space W where you want to find a solution for it. Now the idea would be the following. Define a functional, some functional I that realizes the partial differential equation as a Lagrange equation, right? Now use direct methods to prove that the function, there is a minimizer for the functional. And that minimizer would automatically solve the Lagrange equation. And therefore, the equation would have a solution. Okay. Let's take an example here. Consider the partial equation to be this Laplace equation. Okay. And you can, the functional that realizes this Laplace equation as a Lagrange equation is this functional. And we just saw that it has a minimizer in the previous theorem. Therefore, the Laplace equation has a solution. Okay. I think that's all I wanted to speak.
Thank you very much. That was quite an interesting talk and very useful. And well, on that very important consequence, you speak a little, but that's a great consequence of the direct methods. Yeah, no, the floor is open to questions. If anyone has any questions, so feel free to raise your hand and I will unmute you. Or you can mention in chat and I will unmute you from there.